Formula. So today we'll be solving for the magnitude of the electric field at our point P. So we can start by writing down the equation we'll be needing, which will be our electric field equation. We'll be using a little different one, but it will get us to the same place. So we have our Coulomb constant times Q1, and this is just the source charge, and then it's divided by the distance between our source charge and our test charge. Okay. And since this is the equation we'll be using, we can start plugging in numbers. So our E1, we'll call it, and we'll write it in red. Our E1, we will have our Coulomb constant and the charge of that, which is 4 times 10 to the negative 9, and then divided by the distance between this particle and this. This is our source, and then these are our test sources. So we will have 0.8 squared underneath it. And we will do our second charge, E2, and we get our Coulomb constant times the absolute value, so that just becomes 6 times 10 to the negative 9, all over the distance squared. And to calculate this distance, we just use our Pythagorean theorem to get our hypotenuse. So the r for this would equal the square root of 0.8 squared plus 0.6 squared. And the answer that we get from that is the distance, which will be 1. So then we do our 1, square it, and our answers that we get here, for our first charge we should get 56.2 newtons per coulomb. And then our second charge, we will get 53.94 newtons per coulomb. And just to remember, these are both just the magnitudes, not taking into account direction. And we can also note that on our charge number 2 right here, there will be an x and a y component, so we will have to split this up. Okay, and we can just we'll just split it up on this side, or we'll scroll down. Okay. And just to write out our end formula, so our total electric field will equal our E1, we'll write it in the colors just to keep consistent. So we will have our E1 I hat, and then from that we will subtract our E2 in the x direction. That's also an I hat, because for our E2 in the x, we can see that when we draw our little force body diagram, we do know that positive particles will have the force going out, so there will be a force going this way on our point, and then negative ones will have their force going in, so it will pull it this way. And we can see that the x components of both, which this one's only an x component, actually pulls it in the opposite direction. So we do know that we will have to subtract our x component of charge number 2 from charge number 1. And we will add our y component, which the only one that has a y component is our second charge. So we will have e2yj hat. Okay. And from here we can go by the triangle. We'll just kind of write it out real quick. So we do know that the cosine of theta, since we don't have any angles, but we do have all the side lengths, we know that cosine theta is adjacent over hypotenuse, and then we know that sine theta is opposite over hypotenuse, and we will just consider this to be our theta. So for the cosine we will have 0.8 divided by our hypotenuse, which we did already calculate, and that was 1 all over 1. And then our opposite, which we said was 0.6. And then our hypotenuse, which is again 1. So when we break this up, we will end up with e1 I hat minus our e2 minus our e2 times the cosine theta I hat. And after that we will add on our y component, which is just e2 times the sine of theta. And we did already solve for these, so we can just plug the numbers in, and our final formula should look like this, with the numbers and everything. We will get our E1I, which was 56.2, and then we'll be subtracting our E2 times 0.8, so we do know that our E2 is 53.94 times the cosine of theta, which we said was 0.8. So we'll just multiply that. And that is our I hat. And then when we add on our j hat, we will get our E2 times the sine of theta. And we do know that our E2 was 53.94. And then we know that our sine theta is 0.6. And then that will be our j hat. And once we do all the calculations on the inside of the parentheses, we will get 13.05 I hat plus 32.36 j hat. And that will be our component form of the resultant vector of these two. And if we wanted to find the direction, we know that we will just use the inverse tangent function. So we know that tangent theta equals opposite over adjacent, and then we'll know that tangent of our opposite over adjacent will equal our theta, which is what we want to find. And then we end up with tangent, inverse tangent of our opposite, which we did say was 32.6. Oops. Not opposite over adjacent. It's y over x. Okay. And we have our y being that 32.36. And then we have our x, which is 13.05. And once we do that calculation, we will get 68.04. And that will be degrees counterclockwise from the positive x-axis. And if we also wanted to solve for one more thing, so this is just the component form of that resultant vector, but the original question did want the magnitude. We will just find the magnitude real quick, and we know that is, we're using the a squared plus b squared equals c squared method. So we will just do 13.05 squared plus 32.36 squared, and then we'll square root that whole function to get the magnitude, which when we do that we should get 34.89 newtons per coulomb. So this is our magnitude, this is it in component form, and then this is the degrees from the positive x counterclockwise from the positive x-axis.